Okay, so we have second order linear homogeneous differential equations with constant coefficients. Okay, so what does that mean? So for we'll have a y double prime plus b y prime plus c times y equals 0. Okay, so this is our equation. So on our left-hand side, we have a differential equation. On our right-hand side, we know that it's equal to 0. So this is a homogeneous system, okay? On our left-hand side, we can also see that we have constant coefficients a, b, and c, okay? And then they are multiplied by y double prime, y prime, and y. These are all functions of y. So we describe this as a linear system, okay? And because it is to the second derivative, second order, okay? So for this system, for these types of systems, we assume the general solution y is equal to c sub 1 times y plus c sub 2 times y, okay? So what are c sub 1 and c sub 2? These are going to be our variables for this, okay? So these are our variables for this solution. Kind of looks confusing, okay? So we can go on and we can solve, okay? So we'll have let y equal to a basic, exponential. We'll have e to the rt, okay? So we have our ODE right here, and we'll know that a is not equal to 0. We can't have a equal to 0. So we'll substitute y and its derivatives into the ODE, and we'll get this term right here. We can see clearly that we can factor out e to the rt. And since we know that this won't be equal to 0, we can divide it out. And we'll get this, which is what we call our characteristic equation. We'll have the same constraint. And we can see that this is descriptive of a quadratic equation. We've been solving those since, Algebra 1, okay? So we'll have 3 cases, okay? Our case 1 is R1 and R2 are not equal to each other, but they are contained in the real numbers. So our solution, our general solution that we had before, becomes y equal to c sub 1 times e to the r sub 1t plus c sub 2 times e to the r sub 2t, okay? So what can we do with this? We can plug this into examples, okay? In any given kind of differential equation that fits these constraints that we have right here. So for case 1, we could have something like this, okay? And essentially, we could plug this in, have our characteristic equation. So we'd express this as so, okay? And then we can see that this clearly has factors, okay? So we would have factors r plus 5 in parentheses times r plus 2. So we can see that from this we'll have 2 solutions. We'll have r equal to -2 and r equal to -5, okay? So what can we do with this? Well, we can fill in those values and we'll get a function, we'll get a general solution for this ODE right here that has variables t, c sub 1 and c sub 2, and we can find those values of c sub 1 and c sub 2 using an initial value problem. So if we were to continue, we'll get y is equal to c sub 1 times e to the -5t plus c sub 2 times e to the -2t, okay? And then from here, let's say if we had, if we set our values for the ODE, we'll use the same ODE and we'll use the value y for t of 0 is equal to 1 and y prime for t of 0 is equal to 0. Well, we have this same localized point and we can plug in the values. So we can take the derivative of this guy right here. We can take the derivative of this guy right here, okay? And we can solve, okay? So we'll get something like y prime equal to -5 c sub 1 times e to the -5t plus, or we'll say plus, we'll say minus -2 sub, -2 or -2. Let me just say that -2 sub, or 2 times c sub 2. times e to the negative 2t. Okay, so like we can do from here, we can plug in these values, and just to speak off, okay, so we have t is equal to 0 for both of these, so we know that the exponential parts are going to be equal to 1 for this. So we'll have, for this one, we'll have 1. For this one, we'll have 1 is equal to c sub 1 plus c sub 2. And then for this one, we'll see that we'll have 0 is equal to negative 5 c sub 1 minus 2 c sub 2. And because we know right here with these two expressions of the ODE for the initial value problem, we have a system of equations. Okay, so we can solve that using the same linear algebra. I mean, not linear algebra, just normal algebra. You know, this is like high school stuff. So you could solve these, and you get specific values of C1 and C2, and then you have a specific differential equation that you can express. Okay, so let's move on to the next cases. Let's say we have the same expression, and then case 2 is that we have R1 and R2. They're not equal to each other, but they are complex roots. So R is equal to A plus or minus B times the imaginary root I. So what we can do is we can take this quadratic formula, and we can express R, okay? And we can set Y equal to E to the, this would be R right here. So A plus B times the imaginary root I to the T. Okay, and we know that this is a complex solution. If we were to expand and plug this in, if we were to plug the solution in, and we were to expand, we'll get an imaginary part, and we'll get a real part. And these values will sum out to 0. Okay, so 0 on the left-hand side and the right-hand side. Okay, so we can factor this out, and we'll get this equation right here. Okay. And knowing Euler's formula, which is e to the it is equal to, I think it's cosine, it would be cosine t plus I sine t. Okay, so if we were to use the same kind of thing right here, we can plug it in, and we'll get a real part, e to the at times cosine bt, and then our imaginary part would be e to the at times sine bt. So if we, using the same Euler's formula and our general solution that we had from before, we'll get y is equal to e to the at parentheses c sub 1 times cosine bt plus c sub 2 times sine bt. Okay, and then we'll move on to our third case. So let's say we plug this in, we get our characteristic equation, and we have two equal roots. Okay, so with this, we can express this as a factor r plus a parentheses squared equals 0. Okay, and then we know just from algebra that looks like this. Okay, if we were to simplify it, and we can look at that, and it looks the same as this. If we were to like move it from the characteristic to what we knew it to be before, the normal ODE that we had at the beginning. Okay, so we can already see r is equal to negative a for this equation, and we will use y is equal to e to the negative at, like this is r, and then we'll have u, which is a function of t. Okay, so this is going to be kind of like a substitution. Okay, so we'll have y prime, and then we'll have y double prime. And notice that if you were to multiply this term by a squared, you're to multiply your y prime equation by 2a and have your y double prime stay the same. You can add all of these together, and you'll get the same result as you had over here. Okay, so because you add all of these together, you can see that this is equal to 0. Okay, so you can say the same thing. This is equal to 0, and then you can add all of these together. So this will be 0, these all right here, and then these all right here will be equal to 0, and you will only have this term left over. So we can solve for this. Okay, so now we know that 0 is equal to e to the negative at times u double prime. We know that this is always going to be constant. We knew that before, so we can divide it out. So our solution, if we take the integral of this twice, will be u equal to c sub 1 times t plus c sub 2. And we will get this as our solution if we only look at t. And this will look like, in general terms, we'll have an e to the negative at times c sub 1 t plus c sub 2. And that'll be all three cases of the second order linear homogeneous differential equation with constant coefficients.